So what I would like to discuss today is our final leg in our study of the hydrogen atom. So what I would like to discuss today is what is quantized inside the hydrogen atom. So for an infinite well, now you need to pay attention, come on, stop talking. For an infinite one-dimensional well, of length L, what is quantized? The energy is quantized. So you have these finite energy levels, not equally spaced, but a spacing that is proportional to the square of a quantum number n. So the energy is n square h bar square pi square over 2m L squared. So the energy goes up as n goes up. N is a quantum number, and it's just one quantum number because it's a one-dimensional system. Got it? And the wave functions are also quantized. And you know what the wave functions are, and I think you should remember the wave functions at least for a one-dimensional well. They are given by some constant of proportionality c sine of n by x over L. A 1D infinite well, one quantum number n, which identifies the wave function as well as the energies. What about a 3D infinite well? It will have three quantum numbers. So if I were to draw a 3D quantum well shaped as a cube of length L, width L, height L, and the electron or proton or neutron or whatever particle we're dealing with is trapped inside this infinite well and the potential is infinite outside, then we will identify the energy which is quantized by three quantum numbers, nx, ny, and nz. And the overall energy of a quantum state is now identified by these three variables. Each one of them is an integer, and the energy is given by nx squared plus ny squared plus nz squared into h bar squared pi square 2m L squared. Correct? Three quantum numbers, nx, ny, and nz. Why do we have three quantum numbers? Because it's a three-dimensional system. For a two-dimensional system, if I had a 2D well, I would have two quantum numbers. Some of these energies will be equal, even though the quantum numbers might be different. So those are degenerate energy levels. Now for a hydrogen atom, how many quantum numbers do we get for the wave functions? Up to? How many quantum numbers do we have? Three, which are n, l, and ml. So a wave function for hydrogen is identified by three quantum numbers, n, l, and ml. This wave function no doubt is a function of r, theta, and phi, and it's a product of a radial part which depends upon n and l, and an angular part whose form depends upon L and ML. I think this is how we put ML here and L here, right? Or is it the other way around? I think it's the other way around in the convention that we're using. So we have three quantum numbers, a trio of quantum numbers, N, L, and ML. So in the 1D infinite well, N kind of quantifies the energy of the energy level. In this 3D infinite well, nx, ny, and z quantify the energy. In a harmonic oscillator, which goes like this is the potential energy for a harmonic oscillator. the levels are equally spaced. And the energy of this system is n minus half h bar omega, where n goes from 1, 2, 3 all the way up to infinity. So the quantum number n is quantifying the energy. It's discretizing or digitizing the energy. The energy is now digital. It's not analog. Only precise values of energy are possible. So if you shine light on this harmonic oscillator, and light of course has a wavelength, and the photon that is incident on this infinite well has some energy. If that energy does not match any gap, that photon is going to pass through. That photon will not be absorbed by this oscillator because there is no gap that is in resonance or matches with the incident energy. So this harmonic oscillator will be transparent to that kind of photon. Now in our hydrogen atom we have these three quantum numbers n, L and ml. What do they quantize? So first of all, I would like to focus my attention on this number here, n. N of course goes from 1, 2, 3 all the way up to infinity. L for a given n starts from 0 and approaches n minus 1, and ml for a given L is 0, 1, 2 up till L on the positive side and up till minus L on the negative side. So these are the constraints that we have on these quantum numbers. But what does n really signify physically? What does L signify? And what does ml signify? That's the purpose of the lecture today. So we would like to come up with an expression for the energy for an electron inside the hydrogen atom similar to the expressions for the energy that we have for the infinite well, the 3D well, the harmonic oscillator and so on. Got it? That's motivation for today's lecture. First of all, I would like to find out the meaning of n. Meaning of n. So if I look at the Schrodinger equation, the Schrodinger equation in shorthand time independent form is minus h bar square 2m Laplacian plus the potential energy term, all of this acting on the wave function. The wave function of course is a product of r, capital theta, capital phi, because we've broken down the wave function into these three components, and this equals the energy r, theta and phi. The combination of theta and phi we've also labeled as capital Y. Anyway, this is our time independent Schrodinger equation. So in order to find out the meaning of n, what I would do first of all is look at the smallest value of n. What's the smallest value of n possible? 1. Say my n equals 1. What would be my value of L? 0. What would be my value of ml? 0. All right. Now for if I were to look at the expressions for r, n equals 1, L equals 0, this is a function of r. If you look at the table that I provided to you, does anyone have that table in front of them? This is 2 over a naught cube e minus r over a naught. Correct? What is y for L equals 0 ml equals 0. What is this thing? 1 over? So for this combination of N, L and ML, my ground state is psi N1 L0 ML0 R theta and phi. This is just equal to 1 over, I multiply these two functions, I will get 1 over pi a naught cube E minus R over a naught. Correct? So this is the wave function for the n equals 0 state. I take the radial part and I take the angular part and multiply the two parts together. This is my wave function for n equals 1, which will also have L equals 0, ML equals 0. Now if I put this function into the Schrodinger equation, everything should work. Since this is a solution to the Schrodinger equation, therefore if I were to replace R theta phi with this value, the left hand side would remain equal to the right hand side. So let's do that now. In order to kind of verify that this is a solution, I would need to write down the expression for del square in polar coordinates, and that expression is 1 over r square r let's put this at the very end, plus 1 over r square sine theta partial theta plus 1 over r square sine square theta, the double derivative with respect to phi of the function. Now what is the function? This is my overall function, the wave function. Let's for the time being call this factor C. So my function is C E minus R over A naught. So this is the first term in the Schrodinger equation. I take that differential operator, the Laplacian, and break it down into its polar components. The second term will be the potential energy. So the second term is going to be minus epsilon square 4 pi epsilon naught R C, correct? Now do not confuse this E with this E. This is the charge on an electron, this is the E which is the base of the natural log. Alright, so don't confuse these two E's. This equals the right hand side. The right hand side is the energy which is a scalar in joules multiplied with the function C E minus R over A naught. So this is the new Schrodinger equation. When I insert one of the solutions into the equation, this is what I get. So this must hold true, this must be valid. If the solutions that I found in the previous lectures, they are legitimate solutions, then if I were to put a solution into the differential equation, the differential equation will stand, it will hold water, it will still be true. Now if I look at this equation and I try to compute the left hand side, will this term really matter? Why not? Because there is no theta dependence here. Will this term matter? No. So the second and the third terms in this expansion do not matter for the n equals 1, L equals 0, ML equals 0 wave function. Correct? So I can just ignore these terms for this wave function only. For this wave function, I ignore them. So now what I'm left with is, if I look at the first term is minus h bar square 2m. I just put this r square over here, and I kind of have the derivative r square and the derivative of this thing over here. Which is C E minus R over A naught. Correct? Yes, please.
So why did you remove the 1 over r squared sine theta and 1 over the r squared sine squared theta term?
Because I'm taking a derivative with respect to theta of this function. This function doesn't have theta, so the derivative is 0. Likewise for this term.
So that's what they don't count in the expression then.
I mean, you just kind of act this operator onto this, you'll get 0. So this is the first term, and the second term that survives on the left hand side is this thing. So this becomes minus C E square 4 pi epsilon naught R E minus R over A naught, and the right hand side is E C E minus R over A naught. Correct? So far so good. It's pretty easy here. Now what I would like to do, I would like to compute this derivative. So I just move to this side of the blackboard and I compute this derivative on its own. Let's see what comes out. The derivative of r square followed by the derivative of this thing. C is a constant, and I'm left with minus 1 over A naught E minus R over A naught. Correct? I take this minus 1 over A naught outside, I'm left with minus C over A naught. The derivative of R square E minus R over A naught. Now I do the, probably call this the product rule. I take the I take the derivative of what's inside the parenthesis over here, and the derivative is 2r minus 1 over A naught r square all right. Now I plug this value back here, and I'm left with minus h bar square 2m r square minus c over A naught 2r E minus R over A naught minus h bar square 2m r squared minus c over A naught minus 1 over A naught r square E minus R over A naught plus this term minus C E square 4 pi epsilon naught R E minus R over A naught equals the right hand side, which is the energy C E minus R over A naught. Got it? Yes, please.
The value of ECE minus to the power of minus RA over A naught to 0, इसीलिए हम दोनों equal कर सकते हैं अभी.
नहीं कि कहाँ zero? We haven't put anything. We haven't made any assumptions.
You shifted the C square वाला expression to the right side now.
I haven't shifted anything to the right side so far. This is the left hand side, this term, this term, this term. It still has the c in it. This is not an equation. I'm just computing this derivative. This equals this. All right. Now this is my equation. This has the left hand side and the right hand side. Now c is on both sides, and c cannot be equal to 0. Otherwise the wave function doesn't exist. So I can just cancel out the c's. Is it possible that this expression is 0? This cannot be 0. So I can just cancel this out from both sides. And I'm left with something really simple. H bar square 2m a naught squared, and then I have an r squared, and I also have an r at the top, so I have r, and then I need, this is a minus sign over here, two m a naught squared, right? A naught squared minus h bar squared 2m a naught squared minus e squared 4 pi epsilon naught r. This equals the energy of the electron inside the n equals 1, L equals 0, ML equals 0 state. Now let's try to simplify this a bit further. If I wanted to simplify, are you sure there's a minus sign over here? Plus C to R. So this is positive. Positive will give me a negative number here, negative. Got it? Now, can I simplify this further? Let's look at the expression for A naught. Let's see what is A naught. I always forget what A naught is. यहाँ तवज्जो दो, फिर कुछ समझ नहीं आएगी. So A naught has some value, some expression. I always forget it. It's a Bohr radius. So what I would do, I would use Dr. Niels Bohr's ideas and find out what A naught is. This is from the pre-Schrödinger time, pre-wave function time. So what Bohr did, he looked at the nucleus, he looked at the electron that goes around the nucleus at a distance r. The mass of the electron is m, and he believed that the rotation of the electron around the nucleus was due to the electrostatic interaction, and that electrostatic interaction provided the centripetal force. So the centripetal force for this electron, mv square over r, a totally classical idea, pre-quantum. It's called the old quantum theory. This is the expression for the centripetal force. The centripetal force is going to equal to the product of the charges, which is E square divided by 4 pi epsilon naught r squared. All right, so I can just remove this r here, remove this point. I will have m v square is e square 4 pi epsilon naught r. Now this is a classical concept. What Bohr also proposed, that's why it's called the old quantum theory, is that the angular momentum of this electron is quantized. Even though we'll later see that the electron doesn't have an angular momentum in this state, but Bohr proposed that the angular momentum is quantized. So he proposed that the angular momentum mvr in this state is h bar. All right, is nh over 2 pi. Does it make sense? Nope. So this is the angular momentum of the electron, and Bohr proposed that the angular momentum is quantized in units of h bar. For n equals 1 it's h bar, for n equals 2 it's 2h bar, then 3h bar, and so on. Yes,
How
please.
exactly did he propose that?
It was his he proposed this based on the idea that if I have a circumference of radius r, circumference 2 pi r, then this must fit an integer number of wavelengths. So 2 pi r must be equal to an integer number of wavelengths. Now the wavelength is related to the momentum according to the de Broglie relationship. So P into R is n h bar. P into R is the angular momentum, P is the linear momentum. This is how he was able to reach this conclusion. So it's a combination of his ingenuity and de Broglie's relationship. Anyway, mvr equals h bar, which means v equals h bar over mr. Now take this value of the speed of the electron and put it in here. I get m h bar squared m squared r squared equals e square 4 pi epsilon naught r. So h bar squared m r squared r equals e square 4 pi epsilon naught, which would imply r over mr over h bar square equals 4 pi epsilon naught over e squared, which implies that my r equals 4 pi epsilon naught m e squared h bar squared. All right, but this r, Bohr called this the Bohr radius. This is our a naught. This is the radius of the electron in its lowest orbit. So this is really a naught. So if I look at the first term over here, h bar square m r into a naught. Now my a naught is this thing, 4 pi epsilon naught h bar squared m e squared minus the second term h bar squared 2m a naught squared minus e squared 4 pi epsilon naught r equals the energy. Luckily, this term equals this term. They cancel out. Hence, the energy for this electron in the n equals 1, L equals 0, ML equals 0 state turns out to be really simple. It turns out to be E for the ground state, for the n equals 1 state. So now I put n equals 1 because my calculation takes up the n equals 1 trial wave function. So this energy will be only valid for that particular wave function. All right. So this turns out to be equal to minus h bar squared 2m a naught squared. And this is a precise energy. It's a precise energy. And if you put in the values for h bar, the mass of an electron, the Bohr radius, which is 0.53 an angstrom, 0.05 a nanometer, if you put in these values, this, and you get an answer in joules, you convert it to electron volts, this turns out to be minus 13.6 electron volts. Yes, please.
Sir, are these sort of derivations universal for different values of n or different orbitals?
I'll explain that next. Yes, please.
So can you repeat why did you eliminate those?
The first and
Yeah.
because this equals this. So the m goes away, h bar square goes away, this term equals this term. So this is the energy for an electron inside the hydrogen atom in the n equals 1, L equals 0, ML equals 0 state. If you were to repeat this calculation for other values of n, the L and ML, you will notice that the answer is always independent of L. It doesn't depend upon ML, it only depends upon n. And the dependence turns out to be the following. So you can repeat a similar calculation for higher wave functions. That's a naive way of looking at the quantization of energy. There are more sophisticated ways to do that, which involve taking the expectation value of Hamiltonians, but I'm not going to delve into that. So what you could do next, take n equals 2, L equals 0, ML equals 0. Take that wave function and just repeat the process. You will find out that the energy is minus 13.6 divided by 4. For n equals 3, you will find out the energy turns out to be minus 13.6 divided by 9, minus 13.6 divided by 25, 16, so on. So you can repeat the calculation for higher values of n, and whatever value of L and ML you choose, it doesn't factor into the energy calculation. So the overall, the energy of the electron is determined only by one quantum number, just one, that's n. It's called the principal quantum number, and the energy turns out to be this thing, minus h bar square 2m a naught squared 1 over n squared. The energy is quantized, and the quantum number n determines the value of the energy. So if I were to plot these energy levels on a ladder scale, we can draw a similar energy landscape for the hydrogen atom. Any questions in the meantime? Yes, please.
Sir, could you please summarize this, summarize ये जो सारा calculation है in like 4 to 5 steps orally?
Alright, okay, good point. I have the Schrodinger equation in front of me. I take a wave function. A wave function is the solution to the Schrodinger equation. So if I were to put the wave function into the Schrodinger equation, everything will hold true. The wave function solves the Schrodinger equation. So I take a very basic wave function, which is the n equals 1 wave function, and I just spruce this up into the Schrodinger equation. I throw in this wave function into the Schrodinger equation. Now I have my differential operator, my Laplacian, and my potential energy. I find out the derivatives. I calculate the left hand side and I calculate the right hand side. The two must be equal, and this is the final result that I get. That this is the final thing that I obtain. What this is now an algebraic equation. The differential equation has been converted to an algebraic equation, in which E, the energy of the electron, is now expressed in terms of simple numerical factors. Finally, in the end, the energy takes up a very simple form, this form. Now if I were to repeat the calculation for higher wave functions, the only thing that's going to change is that this form preserves itself and I get an additional factor of n squared, 1 over n squared. By the way, do you notice the similarity between this expression and the expression that we have over here? Very similar. A 2m a naught square in the denominator instead of a 2m l square. Another big difference is that for an infinite well, n square is in the numerator. For the hydrogen atom, n square is in the denominator. But then notice the energy is negative as well. So how do I plot this on a potential? A second. Right, so I need to. Please, you can ask your question and don't mind me. I'm not looking at you, but I'm listening. Please, bolo. ये वाली. So this is, I'm just calculating the Bohr radius. I start off from here. I'm calculating what the Bohr radius is. So I come to here, I go here, finally this is the Bohr radius. So this is a calculation for the Bohr radius. वो equation अभी stand करती. So I just want to put in the value of A into this expression. I don't remember A naught, so I just rederive A naught from first principle. Okay, from the Bohr's model. Yes, please. What L and ML signify? It just doesn't depend upon that quantum number. That quantum number has another significance that I'm going to explain. So if I were to plot the potential energy of an electron inside a hydrogen atom, what would it look like? It goes, it's a hyperbolic function. Depends upon 1 over r. So it looks somewhat like this with minus sign, so it's negative. This is the potential energy function for electron inside the hydrogen. I simply plot this, simply a plot of all right. So really it's a 3-dimensional plot. So I kind of take this function and move it around the z-axis to kind of make a inverted Mexican hat, sombrero hat. right? So this is really in 3 dimensions, something of this kind. All right, they're like a circular well. Now this is the potential energy function, and the ground state corresponding to n equals 1, the energy is, let's call this E naught, let's call h bar square over 2m a naught a square E naught n square. This is the energy in the nth energy level, nth wave function. So this energy is, the lowest energy is here, corresponding to n equals 1. This energy is minus 13.6 electron volts. So an hydrogen atom in the ground state has an electron sitting at minus 13.6 electron volts. What is 0 volts? 0 volts, electron volts, is this energy. This is when the electron has been stripped out of the atom. That's called ionization. So when the electron has been stripped out of the atom, the hydrogen atom becomes a hydrogen plus ion. The electron has been stripped out or ionized. So the minimum energy that is required to ionize a hydrogen atom is 13.6 electron volts. That's the ionization potential of hydrogen. The next high energy level, which is, first excited state, will have an energy minus 13.6 divided by 4, somewhere here. This is n equals to minus 13.6 divided by 4, then minus 13.6 divided by 9 electron volts. So the energy levels will become closer and closer and closer together. So these are the energy levels inside a hydrogen atom. This energy level corresponds to a wave function. That wave function is R, n equals 1, L equals 0, Y, L equals 0, ML equals 0, right? This would correspond to various wave functions, because for n equals 2, L could be 0 and it could be 1. When L equals 0, ML could be 0. When L equals 1, however, ML could be 0, plus 1, minus 1. So really there are 4 quantum states with the same energy. 4 quantum states with the same energy. One of them is called a 2s orbital. These 3 quantum states are called the 2p orbitals, 2px, 2py, 2pz. We've already seen how to plot these orbitals. But these 4 energy levels are degenerate. They are at the same energy. Remember, and the energy doesn't depend upon L or M, it only depends upon N. Likewise, you can find out what's the degeneracy of this level. Here you will have a 3s, 3 3p orbitals and 5 3d orbitals. Degeneracy of this energy level is 8. And all 8 of those levels will have the same energy. All right? 1 3s, 3 3p and 5 3d. How? Because if n equals 3, L can be equal to 0, 1, 2. ML could be 0, 0, plus 1, minus 1. This could be 0, plus 2, minus 2, plus 1, minus 1. 5, 6, 7, 8, 9. All right? Oh, 1 2 3 4 5 6 7 8 9 9. All right, which can house 18 electrons, by the way, because we're not considering the spin of the electron. That's another quantum system. That's another quantum number. Anyway, so these are the quantized energy levels inside a hydrogen atom. Remember, before we take a 5-minute break, one question. When I showed you the spectrum of the hydrogen atom, there was a dominant line in that spectrum, and I asked you to note down the wavelength. Do you remember what that wavelength is, or could you quote that wavelength again? It's about 656 nanometers. Right. So if I were to kind of, where does that line come from? If I were to look at the n equals 3 level and the n equals 2 level, there's an energy gap. If an electron is excited somehow by an electric potential, electric field, or by collision with other atoms, somehow an electron has been excited to this n equals 3 level, it will have some energy. That energy in the third level is minus E naught over 3 squared. Now if the electron that has been excited to the n equals 3 level falls down, it can fall down into different levels. It can fall down into the n equals 2 level or to the n equals 1 level. Suppose it falls down into the n equals 2 level, makes this transition. Here the energy of the electron is going to be minus E naught over 2 squared. Now which of these energies is bigger?
In magnitude or
This is bigger, right? So the energy gap is separation between these energy levels. That energy gap is minus 13.6, 1 over 9 minus 1 over 4. That's energy gap. So an electron falls from a higher energy level to a lower energy level, its energy, the energy of the atom goes down. The electron were excited somehow in the past to the n equals 3 level, now it falls down to the n equals 2 level, the energy has gone down, the excess energy has to go out. That excess energy goes out as a photon, and I'm going to show after the break where does that photon come from. That photon goes out and that photon carries this much energy. All right, and if I were to find out this energy equals hc over lambda, and from here you can find out the wavelength of this photon. That photon will have a wavelength about 656 nanometers. So whenever the end point of this transition is equal to n equals 2, you can have a transition from n equals 3, n equals 4, n equals 5, you get different wavelengths. Higher the gap, shorter will be the wavelength. But all of these emissions that end at the n equals 2 level are in the visible regime. They form the Balmer series. If you have transitions that end in the n equals 1 level, you get the Lyman series, and all those wavelengths are in the ultraviolet regime. So let's take a 10-minute break and then I'll answer your questions. So I have to cover two more things. One thing is kind of neat, and it's the idea of the photon and how does it relate to superpositions and these energy levels. So the basic idea of the photon Very basic idea. Now the idea of photon is very multilateral, it's very multidimensional. There is many different possible viewpoints about the photon. So one cannot do justice to the meaning of the photon in about 15 minutes. It requires a full course in quantum electrodynamics, quantum optics perhaps. The photon does not have a wave function like an electron or a proton. It doesn't have a position operator. It's a kind of a strange particle. But how does it all gel into the concept of the hydrogen atom? Suppose in the hydrogen atom I have two energy levels, and the electron makes a transition from a higher energy level to a lower energy level. Okay? Suppose this is my initial state, here is my final state. This wave function, let's call it psi initial. Alright? Initial means some value of n, l and ml. Let's call this state psi f, the final state. Now electron makes a transition from the initial state to the final state, and the argument is that a photon is emitted, right, of energy delta E. This energy is I E initial, this energy is E final, and delta E is E I minus E F. Now one way of looking at the photon is that a transition between two energy levels is really a superposition of two quantum states. Alright? Now quantum states can have superpositions corresponding to this energy level. There is a quantum state psi I, there is a quantum state corresponding to this wave function which is psi f. So these wave functions can also be expressed in terms of a superposition. So the idea is that a transition between levels is best expressed as a superposition. Now I'm really happy that we're talking about superpositions today, because probably we started usage of the first word of this word in our very first lecture. So if our system, when it is in a state of a transition, it's making an optical transition between two levels, is in a superposition, I can write the wave function for this. A wave function for the superposition will be the sum of these terms. But the wave function also has a time dependent part. When we take superpositions of these solutions to the Schrodinger equation, we cannot ignore and bypass the time dependent part. So if I were to write big psi for the initial state, which has a space part as well as a time dependent part, what will this look like? What is capital psi I equal to? It's the spatial part multiplied with the time dependent term. What is the time dependent term? Now we are kind of invoking the time dependent Schrodinger equation. Anyone? Any guess? So I mean, the wave function has a space part and a time dependent part. This is a space part. What's the time dependent part? Mohammed? Sorry?
Exponential function of time.
Of what kind of time? So E raised power
Minus iota.
energy. Which energy? Initial energy. Correct? Likewise, I will have, this is a time dependent wave function which depends upon both space and time. So it depends upon r, theta, phi and time, right? Because this depends upon r, theta and phi. So this is psi f E minus iota E f T over h bar. Now what's the total wave function in a state of superposition? I just add up these wave functions, right? That's what if I were to make an equal superposition, I would kind of write psi r theta phi time is a sum of these wave functions with the 1 over under root 2, right? Because I need to normalize. So this is 1 over under root 2 psi I e minus plus psi f correct. This is the superposition. So when an atom is in a state of emitting a photon, emitting some kind of radiation, the electron is making a transition between two levels. The quantum wave function for that atom or electron in that state is best written down as a superposition, and it makes sense. Why? I'm going to show this to you in a minute. So this is my superposition quantum state during an optical transition. Now for this quantum state, let me find out the probability density function. That will be the modulus square of this superposition state, and that will tell me where can I find the electron, where is the density of charge inside the atom, and is that density of charge time dependent or independent. Now the question is, in the Schrodinger's model of the hydrogen atom, the energy levels are spaced apart and there is no reason why an electron from one energy level would like to change its energy level, because these are solutions to the Schrodinger equation. If these are solutions to the Schrodinger equation and you put an electron in energy level, it must remain there forever. So what nudges the electron to come down? So this is a deep question. Actually what nudges the electron to come down is 0 point energy in vacuum. Vacuum fluctuations make the electron make these downward transitions. But this is a reserve for some advanced topics in quantum electrodynamics. But it's really spontaneous emission from vacuum that causes an electron from a higher energy level to come down to a lower energy level. So if I were to take this wave function during an optical transition, this superposition, and find the modulus square of this wave function, let's see what I get. So psi, big psi mod square. I want to calculate this thing, the probability density of the electron when it's making a transition. And this really tells me the charge density as well, because the electron is charged. So this is also the charge density, and I want to see if this is time dependent or not. And if it is time dependent, what is the time dependence? So if I were to take this, how do I find the modulus square? I take the wave function, complex conjugate, and multiply it with the wave function itself. So now if I were to kind of take the complex conjugate, first of all let me write down this thing. This is psi I star E plus I E I T over H bar plus psi F star E plus I E F T over H bar multiplied by psi I E minus E I T over H bar plus psi F correct. Now this becomes 1/2. Now I do the multiplication. When I multiply this term with this term, the exponents go away and I'm left with psi I mod square plus, when I multiply this term with this term, the exponents go away and I'm left with psi f mod square. When I multiply this term with this term, let's see what I get. Plus psi I star psi f e minus I e f minus e I t over h bar. Correct? Plus another term. That other term is psi I psi f star e plus I e f minus e I t over h bar. Correct? Now this, is this real? Is this thing real?
Yes.
Does it have any time dependence? No. Real?
Yes.
Time dependence? No. All the time dependence is in here. All of it is here. Now if I were to, now this term here and this term over here, are they complex conjugates of one another? Yes, they are. So if I were to take this term and find the complex conjugate of this term, I would get over here psi I star psi f complex conjugate of this. So now I have a term and its complex conjugate added up. So what will be the sum of a number, complex number, and its conjugate equal to? Twice the real part of this number. Right? So I'm left with half psi f mod square plus psi I mod squared plus real part of psi I psi f star e plus I. Now I can put ef minus ei equal to delta e. That's a separation between the two levels. And I can put delta E equals to h bar omega. Omega is the frequency, is some frequency. So this becomes omega t. Yes, please. So I'm defining delta E is EF minus EI. All right. This equals h bar some omega, some frequency, right? That's it. Omega is a frequency. Now this is my time dependent term over here. If my psi I is real, my psi f is imaginary, then psi f star is real. So this is real. Then I take the real part of this, I'll get a cosine omega t term. So depending upon whether these are real or imaginary, I'll get either a cosine omega t term or a sine omega t term in my answer. Now this is a radiating, this is a charge, a probability density function that is oscillating in time. Now, please pay attention to this. Do you agree with me that all the time dependent part is in this term? It's hidden over here. Now this term will be proportional. What's the real part of ei omega t? Cosine of omega t. What's the imaginary part? Sine omega t. So this will either be cosine omega t or sine omega t or a combination thereof, depending upon whether these are real or imaginary. But it will always have a time dependence of the form omega t. If I were to write this in general form, this term will have some magnitude a. I'm only considering the time dependent part, only this term. this will have some magnitude a, and cosine omega t plus some phase perhaps. Yes, please. Yes, please. Suppose my psi I is some C1, let me finish here, C1 EI phi 1, correct? This is a complex wave function. It's going to have a real part and an imaginary part. The general form of psi I is this, right? Psi f general form is some C2 EI phi 2, correct? So if I just look at this term, which is the only time dependent part in the probability density function, I'm left with C1 EI phi 1 C2 EI phi 2 EI omega t, correct? So far so good? Excuse me, I want to take the real part of this. Correct? C1 and C2 I've defined to be real, and I've put all the complexity in the phase factors phi 1. So C1 and C2 are real, and I want to find the real part of E I omega t plus phi 1 plus phi 2, correct? Now what's the real part of this function? So all of this I can lump this into some other constant a, cosine of omega t plus phi 1 plus phi 2, and I can call it phi. So the time dependent part of the probability density function, what does it physically correspond to? What is the probability density function for an electron? If you want to measure it in an experiment, what are you really measuring? You're measuring the charge on an electron. One way to measure an electron is the charge on an electron. Wherever the electron is, higher will be the charge will be there. So it's really the density of the charge that you're measuring. Got it? So an electronic probability density function inside a hydrogen atom really corresponds to the charge density of the electron. Where does the charge lie? Because an electron is manifest by its charge. ऐसा ही है ना ये बात कि जहाँ electron होगा वहीं charge होगा. So it's really the charge density of the electron that you're looking at. Now you have a charge density which is oscillating in time. Whenever an electron is making a transition inside a hydrogen atom, the charge density fluctuates in time. If I were to plot this oscillating charge density, psi mod square, if I multiply this with the charge on an electron, which is E minus E, this object is called the charge density. Now the charge density is time dependent because the charge of an electron is really oscillating. When an electron's wave function is oscillating, the probability density is oscillating with time. It's really the charge that is oscillating. If I were to plot this function will have a time dependence and it will have a frequency omega. That frequency is proportional to the energy gap. Now if I were to, what does an oscillating charge do in time? What does an oscillating charge do? So if I have a charge, suppose I'm a charge. Oh, yes. So if I'm oscillating in time, what am I going to do? Classically, I'm going to radiate energy. An oscillating charge radiates energy, electromagnetic energy, electromagnetic radiation. Let me give you an example. Suppose I have two pieces of wires shaped in the form of a broken punctuated T. So one wire like this, one wire like this. It's like a T, punctuated or broken T, the copper wires. And I connect these wires, the ends of these wires, to a function generator, right? A signal generator, a function generator that produces a cosine wave or a sine wave of frequency omega. So this is a cosine omega t function generator. Now what? Now you have a piece of wire connected to a function generator. The charge on this wire, so some charge here and some charge here. At some later time, since this is an AC frequency, this of frequency omega, the positive end becomes negative, the negative end becomes positive. This becomes negative, this becomes positive. At time t equals 0, all of it is neutral. So this positive and negative charge oscillates, right? This will emit radiation, an electric field, and the frequency of this field is going to be omega. This object is called an antenna. So the atom now is acting like an antenna. When an electron is making a transition, the atom, due to its transition, due to the superposition of the wave functions, is emitting radiation of the same frequency omega, which is proportional to the gap between the energy levels. The atom becomes a tiny radiator, a dipole antenna that is emitting radiation, and that radiation is what we call a photon. So that radiation is a photon. All right, good. So this is what I wanted to talk about photons. So any questions about this before I move on to the last part on discussing the meaning of L and ML? Yes, please.
Sir, going to the middle word. So when we go to the middle word, you only write the real part of psi I and psi f star. So why don't we count the psi I star and psi f expressions?
So you can take either the real part of this or this. Is the same.
The real part of both of them, but
So this is a rule that if you have z complex number and you add to it its complex conjugate, this is 2 times the real part of z or 2 times the real part of z star.
oh, so they're both the complex conjugates of each other.
They are, aren't they? They are. 2? Yes, please. All right, so this is a very important question. Is the photon particle radiation, is electron a particle or is it a wave? We don't know. It's both. Likewise, the photon is both. It has wave particle duality. It's also called a quantum field. It's a wave function. So it's both. It interferes, so it acts like a wave at that point in time. A photon can interfere, it does interfere. All right, so what will emit radiation? An electric field. and the frequency of this field is going to be omega. This object is called an antenna. So the atom now is acting like an antenna. When an electron is making a transition, the atom, due to its transition, due to the superposition of the wave functions, is emitting radiation of the same frequency omega, which is proportional to the gap between the energy levels. The atom becomes a tiny radiator, a dipole antenna that is emitting radiation, and that radiation is what we call a photon. So that radiation is a photon. All right, good. So this is what I wanted to talk about photons. So any questions about this before I move on to the last part on discussing the meaning of L and ML? Yes, please.
Sir, go to the middle word. So when we go to the middle word, you only write the real part of psi I and psi f star. So why don't we count the psi I star and psi f expression?
So you can take either the real part of this or this. Is the same.
The real part of both of them, but
So this is a rule that if you have z complex number and you add to it its complex conjugate, this is 2 times the real part of z or 2 times the real part of z star.
oh, so they're both the complex conjugates of each other.
They are, aren't they? They are. Two? Yes, please. All right, so this is a very important question. Is the photon particle radiation, is electron a particle or is it a wave? We don't know. It's both. Likewise, the photon is both. It has wave particle duality. It's also called a quantum field. It's a wave function. So it's both. It interferes, so it acts like a wave at that point in time. A photon can interfere, it does interfere. All right, so what is the meaning of L and ML? Sorry? So this is just a constant. This has no time dependence. So I'm this part. किस इसको psi f star लिया. इसका कॉन्जुगेट चलो यहाँ माइनस आएगा, सॉरी, ठीक है, थैंक यू. All right, so the electron, now there are complex ways of showing this as well. If I were doing a course in proper quantum mechanics, I would do it differently. But now with the machinery that we have built, I'm trying my best to describe the meaning of L and ML only if you can stop talking. Now if I have the energy of an electron, I've seen that the energy of an electron can be broken down into 2 parts. One is the potential energy, the other is the kinetic energy. So I know that my energy has 2 components. So this is my wave function psi. This term h bar square 2m del square acting on psi plus the potential energy acting on psi gives me the total energy. Now if you look at my derivation for the energy of an electron in a certain ground state, what I did, I took the value of the wave function and put it in and did an explicit calculation of the left hand side, and luckily the wave function did not have an angular part, so my calculation was easy. However, this idea can be extended. Remember that this is a number and energy is a number in joules, it's a scalar, it's not a wave function. So this energy must have a kinetic component and a potential energy component. This term gives me the potential energy component of the wave function of the electron when it exists in that wave function. Therefore, this component gives me the kinetic energy. However, I broke down this wave function, this operator into a radial part and a theta phi part. So if I were to do that again, I will have minus h bar square 2m r square r square minus h bar square over 2m r square 1 over sine theta plus 1 over sine square theta all of this acting on psi plus V acting on psi gives me E acting on psi. Now it turns out that this term has only radius in it. This term and this term have theta and phi in them. This is a potential energy term. So can I break down the three terms in the kinetic energy to two distinct components? So what about this term here? 2m r square so this term really corresponds to pr square over 2m. Don't be worried if you don't really understand this fully, but this kinetic energy in the radial sense is equal to the momentum squared over 2m. What kind of momentum is this? Is this linear momentum? For radial energy, is this linear momentum? It is radial, pr square. Now if I look at this expression over here, can I write this in terms of some momentum square over 2 times something for a classical object? For a classical object that is translating, the kinetic energy is p square over 2m. What is the energy of a rotating object? What's the corresponding expression for a rotating object? So L squared over 2 moment of inertia, let's call it I. Alright, so this is the rotational kinetic energy of a classical object. Now does this expression somehow look similar to this? what kind of conceptual connection would you need to make this expression in big brackets look similar to this? What is I for an electron? What is the moment of inertia for an electron that is rotating around the nucleus? Mr squared. So I already have 2 mr squared inside the denominator. So what does this, all of this look like? This must be an angular momentum squared operator. And when we were solving the angular part of the wave function, we put all of this equal to a constant. That constant was L into L plus 1. You have to look up your notes for that, right? So all of this expression really means L square, and that L square equals all of this, whatever I've written in this big circle, minus h bar squared 1 over sine theta, partial theta, sine theta, plus 1 over sine square theta, and when this acts on a wave function psi, which is a solution to the Schrodinger equation, all of this must equal L into L plus 1 h bar squared psi. So this small l, yes, just a minute, this small l is a quantum number. What does it represent? If I take this small quantum number L, multiply it with L plus 1 and multiply all of this with h bar square, I will get the angular momentum of the electron's magnitude squared. So what have I done? Let me recap. The first term represents the radial kinetic energy. The second and third terms therefore must represent the rotational kinetic energy. The rotational kinetic energy has this form, L square over 2I. And I compare this form with the second and the third terms, it appears that I already have a 2, I already have the moment of inertia for the electron. The remainder must be proportional to the square of the angular momentum operator. Alright. Now I've already seen when I derived the angular part of the wave function, I showed you that long lengthy Prowl calculation. I put this value equal to L into L plus 1. Now it's coming to see the daylight. This means that if I have this operator act on the wave function, I will get this number L into L plus 1 h bar square. This L into L plus 1 h bar square thus represents the angular momentum modulus square of the angular momentum. So if I were to take the angular momentum of the electron, I had a spin angular momentum by the way for an electron, now we're talking about the orbital angular momentum of the electron. If I take the angular momentum of this electron and find the modulus square of it, see there's a square over here, so it's really the modulus square of the angular momentum of the electron. This is also quantized, and it's quantized according to the quantum number L into L plus 1 with an h bar square factor. So whatever the wave function of the electron is, I see the L value of that wave function, and the electron will have an angular momentum that corresponds to L into L plus 1 h bar square. Therefore, if I have an s orbital an s orbital has L equals 0. It could be 1s orbital, 2s orbital, 3s orbital. So an s orbital has L equals 0. The modulus square of the angular momentum is 0. So such an electron does not have an orbital angular momentum if it's in the s orbital. Now this breaks and shatters our concepts that we learned from Chem 101, all pre-quantum physics, university physics, college physics, because you really think about the electron as going around the nucleus, even if it's in this lowest energy level. But now you have an angular momentum which is 0. So if an electron is in the 1s orbital, 2s orbital, 3s orbital, you stop picturing the electron as going around the nucleus. Its orbital angular momentum is 0. It must be 0. It can still have spin angular momentum, but its orbital angular momentum in any s orbital, 1s, 2s, 3s, is 0. Now how does all of this make sense? So consider a nucleus. We've already drawn the radial wave function modulus the probability density for a 1s orbital. It peaks at 1 a naught. So really this is a picture of the electron cloud density, the probability density, the radial probability density of the electron. So an electron is not really going around the nucleus. The wave function is spread out. Somehow it tunnels through the nucleus. It's everywhere. So we must stop thinking about the electron. If we were believers in the quantum formalism of nature, we would stop thinking of the electron as really going around the nucleus. The electron is represented by a wave function spread out in space. And at best we can draw the probability cloud for that electron, the radial probability density or other kinds of wave functions. What does the third quantum number ml represent? Now, the third quantum number is something I could simply kind of show. It's easier. So if I do know that my azimuthal wave function depends only on ml and is equal to ei ml phi. All right. So if I were to take the last term over here, phi square of this function, I will get minus ml square of the function. Now if I look at the z component of an angular momentum, Lz, now what is Lz equal to? Lz equals r crossed with p, right? A classical relationship, tensor product, and its z component. All right. So this really equals x py minus y px. But in quantum physics, we've seen that the momentums are represented by derivatives of x. So px is represented by minus iota h bar derivative with respect to y. This is py plus iota h bar y. Now if you don't fully understand this, don't worry. So if you look at this expression and write this in a form which gets rid of the x, y's and z's and puts this into theta, phi and r, this is something that you would get. So I need to explain this, but I don't have the time for this, unfortunately. So this quantum number ml really represents the z projection of the angular momentum. The z projection of the angular momentum is also quantized, and it's quantized according to ml h bar. Probably I'll do a 15-minute kind of doodle on a digital board and upload this last bit so that I can explain this better. I don't have time. I know you're going to rush out in 3 or 4 minutes. So ML really tells us that the z component of the angular momentum is quantized. Now, one last diagram that I would like to draw to explain this further is the following. Suppose L equals 1. What are the possible values of ML? 0, plus 1 and minus 1. Now, an electron is in this state, so it has a wave function y, L equals 1, and ML could be either of these. What I would like to look at is the angular momentum of this electron. The angular momentum is a vector, so I should be able to draw the vector. So what's the magnitude of the angular momentum for this electron? The magnitude comes from here, all right? So this magnitude is under root 2 h bar. I've taken the square root of that thing. So this is the length of the orbital angular momentum, the magnitude of the angular momentum in joule seconds. It's a very small number, h bar, very small. And what are the possible values of the z component of this angular momentum? ML h bar. ML h bar. So it could be 0, it could be h bar, or it could be minus h bar. Now I want to draw a vector. This is my circle. If I were to draw a vector of length under root 2 h bar, I can draw a circle, right? So this is my x, my y axis, my x axis pointing outward, the z axis. So I want to draw a vector whose length is under root 2 h bar. So at the origin I draw a vector that could be anywhere on the circle. The radius of the circle is under root 2 h bar. But I'm constrained by the z component. My z component can only be 0 if my z component is 0 for the angular momentum. What direction could my angular momentum point in? Or any xy, but z must be 0. So I could be anywhere on this xy plane and still keep my angular momentum length equal to square root 2h. So I could be anywhere on this plane. Anywhere on this plane. But I could also be at a z at an angle such that my z component is h bar. Now all of this is square root 2 h bar, 1.4 of h bar. So 1 h bar will lie somewhere here. So I could, my angular momentum could also point at this angle, and it could be anywhere on this cone. So if I were to take a vector on this cone, this vector would still have a length square root 2 h bar, which is the magnitude of the angular momentum, but its z component is constrained to be h bar, right? So if this angle here were theta m, cosine of theta m is this projection here, which is ML h bar, and the length of this hypotenuse, which is L into L plus 1 h bar. The h bars go away, and ML is plus 1 over here, 1 over under root 2, which means that theta m is 45 degrees. But my theta m could also be on the other side, because my ML could be minus h bar. So I could also have my orbital angular momentum pointing on this cone. here. So not only is the energy quantized, the angular momentum of the electron is also quantized. The angular momentum cannot point in an arbitrary direction. It has to be of fixed length, depending upon the value of L, and fixed orientation. Space also becomes quantized. All directions are not the same for the electron. So the isotropicity of space is broken. But how does an electron know what is the z-axis, x-axis, or y-axis? By default, it doesn't know. You have to break the symmetry to define a z-axis, which means you might have to apply an electric field or a magnetic field to break the symmetry so that the z-axis is defined. For L equals 2, you will have a scenario that looks like this. L equals 0, L equals 1, ML equals 1, H bar, 2 H bar on the other side, and you can have these cones. So the space is not symmetric any longer. The angular momentum now becomes quantized as well. So what I'm going to do, I'm going to write on a digital board a proper derivation of this idea and of this idea, just to give you an example. Now I want to finish off this course by a small prayer. During this semester, all of us have really been touched and really moved by what's happening to the world. So I want to stop with a prayer for Palestine and for all the oppressed people in this world. And there's a Palestinian poet with the name Mahmoud Darwish. His grave could be found in Ramallah, and he wrote a very beautiful poem. It's in Arabic, but the one verse that I really like is, and in Arabic it is, وَمِنْكُمْ دَبَابَةَ أُخْرَى وَمِنَّا هِجَرٌ. For you, there is another tank, and with us, there is another stone. So thank you very much. See you on Thursday with the quiz.